Hello and welcome to section 5.2 on the definite integral. In this section, we continue exploring the area problem. If you have not seen the previous video on approximating area, then I recommend taking a couple of minutes to watch the video from section 5.1. Take a region R that is formed by a positive function f of x, the lines x equals a and x equals b, and the x-axis. Our goal is to determine, not approximate, the area of R. In the section 5.1 video, it was shown that the area of R can be approximated by taking familiar shapes, which have easily measured areas, such as rectangles, and tiling over R. The result is that the sum of the area of the rectangles is near the actual area of R. It takes 3 steps to determine the actual area of R. Step 1. Predetermine the number n of rectangles you would like to use in your tiling. To create uniformity, we divide the x-axis between x equals a and x equals b into n equal length segments. Each segment will have length b minus a over n, and we will denote this length by delta x. As we need the points in the future, we name the location of the cuts as x1, x2, all the way to xn. Step 2. We look at each individual cut segment. In the ith segment, those points which lie between xi minus 1 and xi. We choose a single x value, call it ci, I, so we know which segment we are choosing from, and plug it into the equation for f. This finds the height of the rectangle. We now use the base of the ith segment and f of ci to create a rectangle. If we repeat this, we will find ourselves a rectangular tiling of R. Step 3. We can calculate the area of each rectangle. Since the cuts along the x-axis are uniform in length, each rectangle has the same base, delta x. The ith rectangle has the height f of ci, where ci was the point chosen along the base. The area of the ith rectangle is f of ci times delta x. It follows that the sum of the areas of the rectangles approximates the area of R. Such a sum is called a Riemann sum for the mathematician Bernhard Riemann. Look closely. Notice that the approximation becomes more accurate as n, the number of rectangles, is increased. In general, the thinner the rectangle, the smaller the error. The exact area of R results from taking the limit of the Riemann sums as n approaches positive infinity. We define the definite integral of a function f between the boundaries a and b to be the limit of the Riemann sums of f as n approaches infinity. We attach the word definite to integral as we are interested in f on a defined interval. Later in this chapter, we will encounter indefinite integrals, which are integrals over an interval that has yet to be defined. If the limit of the Riemann sum exists, then the function f is said to be integrable on the interval ab. Not all functions are integrable, however, all continuous functions are integrable. You most likely will be intimidated by the definition of the definite integral. After all, it is a scary-looking limit involving a sum with an ever-increasing number of terms. Fortunately for all of us, the more we learn about integrals, the easier it is to bypass the limit and compute using special rules. Recall how quickly limits disappeared from our derivatives. Though we will be hiding the limit, you must never forget the basic foundation of the definite integral. It represents area. To be more specific, it represents signed area. More about that in a minute. In class, you will exploit the concept of area to learn more about integrals, such as the ability to calculate the integral of a constant function. The graph of a constant function c is a horizontal line. The area under this line is just a rectangle with height c and base b minus a. Therefore, the definite integral of the constant function c over an interval ab is just c times b minus a, the height times the base. We can take advantage of the cutting and gluing properties of area when calculating definite integrals. The integral of a function f on the interval ab represents the blue region. If we cut the x-axis at a point c, we obtain the red and green regions, whose area, which we represent as definite integrals, sum to be the blue region. So far, we have described the integral as representing the area under a function, but this is not 100% accurate. There are two types of area, signed and unsigned area. It is correct to say that the interval represents the signed area under the curve f. That is, the area above the x-axis is counted as positive, while the area below the x-axis is negative. Often, signed area will be called the net area, and the unsigned area will be called the total area. You calculate the total area by integrating the absolute value of a function, while net area is calculated by integrating just the function. You've seen the basics. Now work towards mastery through practice and study.